Hi, my name is Ian Tobasco, and I'd like to talk to you about a probabilistic approach to inverse convection diffusion. This summer, I've worked with Professor Krzysztof Witkowski from the Aerospace Department. Imagine a terrorist bomb being released near a city. It lets off a cloud of gas, which moves into the city, starts infecting people, and we have sensors littered around the city that pick up different values of concentration. Two important questions that politicians and scientists need to answer before taking next steps is one, where did that gas come from? And two, where is that gas going? My project asks these two questions. First, where is that gas going? That's known as the forward problem, as we know the initial conditions and we're looking for the future evolution of the gas. So let's take a look at this next slide. This is the initial conditions. You can see that the gas looks like a bell-shaped cloud. It's only in one dimension for simplicity. Its mean is at 0.5, or half of the domain. Its standard deviation is 0.1, or a tenth of the domain. And its amplitude is 5. In the future of this presentation, we're only going to be looking at 0.5 and 0.1, mu or sigma, of those two values to see what happens. The forward solution looks like this. Using finite differencing, we see that it convects and diffuses on a periodic domain where everything exiting from the right re-enters onto the left. Here it resets itself to its original conditions. Of course, that only took 0.07 seconds on a computer to solve. It's very simple to do the forward problem. But the more interesting and complicated question is, where did that gas come from? That is, given a finite number of sensor readings from the end result, we want to invert and find the original conditions, mu and sigma, that led to that gas. So let's take a look at the next slide. Remember, we take a probabilistic approach, meaning that we evaluate a conditional probability given our sensor readings of the initial conditions. If we look at the axes on these slides, we see mu is on the bottom, sigma is on the top. This is a contour map showing isoprobabilities. At each level, we increase probabilities until the center where we have a sharp spike in probability. You can see that the most likely values of where this came from were 0.5 and 0.1. This is exactly what we wanted to recover. However, this is a long and a bad way to solve this problem because it requires evaluating every single point on that graph and looking for contours after evaluating every single point. There must be a better way to solve the problem. So if we go to the next slide, we see we have what we call MC-MC updates. This is a random sampling method, otherwise known as a Markov chain Monte Carlo process, where we take any initial condition that a user can guess, and we take random walks around the parameter domain until we find the probability distribution. You can see it took about 1,000 samples to converge to the probability distribution. That is, we start at 0.3, and we end up at 0.5 and 0.1 for mu and sigma, where we just hover for the rest of the time in our random walk, gathering information about our probability distribution. Going to the next slide, I've zoomed in to that part where we've converged. And you can see it's indeed random noise. All we're doing is taking a random walk around the distribution, recovering data. Finally, we have a histogram of our walk. The highest frequencies correspond to, indeed, the most likely answers, 0.5 or 0.1, like we've been saying all along. This solves the backwards problem. Future work includes expanding to 2 or 3 dimensions and asking questions such as what happens if we involve higher order schemes, or what's the best sensor placement to have. Thank you.